So, up till now, we have learned all the elementary transformations in matrices. Now, let's move on to learn what is inverse of a matrix. Before that, let's take an example of a linear equation. 3x is equals to 8. Here, the coefficient of x is 3. So, in order to find the value of x, what do? We multiply this coefficient of x with the reciprocal of its coefficient on LHS and RHS. So, the resultant equation will be 3 into 1 by 3 into x is equals to 8 into 1 by 3. So, by doing this, we get rid of the coefficient of x as 3. We get the coefficient as 1. So, the equation gets transformed into 1x is equals to 8 by 3. Thus, we get the true value of x. In the similar fashion, let's take a matrix equation. Ax is equals to b. Here, the matrix A and B are known matrices and x is unknown. So, in order to find this unknown matrix, what can we do? Here, we cannot write x is equals to b matrix by A matrix because in matrices, division is not possible. Because they are mere rectangular arrangement and a rectangular arrangement cannot be divided by another rectangular arrangement. So, can we apply this concept of reciprocal, like suppose A multiplied by 1 by A x is equals to B into 1 by A or 1 by A into B. If we use this concept of reciprocals, it is first of all not applicable, and even if it was applicable, then we wouldn't be sure whether to pre-multiply it or to post-multiply it, because in matrices, commutative property doesn't apply. That is, BA is not always equal to AB. So we would not be sure whether the value of x is B multiplied by 1 by A or 1 by A multiplied by B. So here we would get two values and we wouldn't be sure whether which one is the true value of x. So this is where the concept of inverse of a matrix comes into picture. So let's take the same example. Ax is equals to b, where x is the unknown matrix. Now, somehow due to elementary transformations or any other method, we find a matrix C which satisfies the relation CA is equals to AC is equals to I, where I is the identity matrix of the same order of M as that of A and C. Then this C can be said to be inverse of A, that is, this C nullifies the effect of A such that C when multiplied with A either in prefix or in postfix, it gives an identity matrix. So what is an inverse of a matrix? It is just a matrix that nullifies the effect of the original matrix. And the resultant is identity matrix. Now, one of the important point to be noted in inverse is only valid for square matrices. However, some partial inverses do exist for non-square matrices, but it is the out of scope of our syllabus. So let us focus only to this, that is for the inverse of square matrices. Now, if we need to find the value of x over here and c is the inverse of a, then we must pre-multiply this inverse in LHS and RHS. That is, the equation should be CAX is equals to CB. Now, why to pre-multiply this C in both LHS and RHS? We will see in the next slide. Now, we will just see the analytical proof of why this C matrix, which is the inverse of A, must be pre-multiplied in LHS and RHS. Now, as I earlier said, the inverse exists only for square matrices. So, let's assume A is a square matrix of order m by m. This implies C2 will be the square matrix of the same order. Now, for matrix multiplication between A and X to exist, the number of rows in X matrix should be equal to the number of columns in the A matrix. So, this is A matrix of order m by m multiplied by X matrix of m by p. Here we have equalized the number of columns in A matrix equal to number of rows in X matrix, so that matrix multiplication do exist, otherwise this equation will be redundant, is equals to now B matrix. What will be the order of B matrix? It will be m multiplied by p. Therefore, the B matrix will have the order m into p. Now, if we pre-multiply this C in LHS and RHS, let's see what happens. C matrix has order m by m multiplied by A matrix has order m by m. This whole is multiplied with X matrix of m by p, which is equal to C matrix into m by m multiplied by B matrix of order m by p. So, this multiplication of these square matrices will naturally come out to be a square matrix, let's say AC, of the order m by m, and this X matrix of order m by p, which is equal to C matrix of order m by m and B matrix of order m by p. In this case, the matrix multiplication in both the sides are valid, since the number of columns in AC matrix is equal to number of rows in X matrix, and number of columns in C matrix is equal to number of rows in B matrix. This AC matrix is subsequently reduced to identity matrix of order m by m, and identity matrix into any matrix is always equal to the same matrix. So, we would get a unique value for X, that is C m by m multiplied by B m by p. These are the orders. Now, let's take a case where C is multiplied after A and after B, that is post multiplication of C in LHS and RHS. So, now we will see what will happen if we post multiply this C matrix in LHS and RHS. So, A matrix has order m by m, it is post multiplied by C matrix m by m multiplied by X matrix of order m by p, which is equal to B matrix of order m by p multiplied by C matrix of order m by m. Now, this will subsequently reduce into identity matrix, and identity matrix into X matrix will give us X matrix of order m by p. Now, let us see the RHS. For matrix multiplication to exist, the necessary condition, as I specified earlier, was that number of columns in the previous matrix must be equal to the number of rows in the preceding matrix. But here the number of columns is P and number of rows is M. So these are not same, and the basic condition for a matrix multiplication to exist is not satisfied. Hence, this RHS becomes redundant and there is no value for this X matrix. Thus, we cannot get a value for X matrix by using post multiplication of the inverse matrix of A. Hence, we always pre-multiply an inverse of a matrix.